So during our lectures in CS50 so far, we've talked a bit about binary and we've talked about why we use it in a computer, but we haven't really talked in that much depth about how it's actually stored in a computer and how different types of numbers like integers or floats, and as we'll learn, there's different types of integers, different types of floats. We really don't know how that's physically stored in the computer at the moment. That's what we're going to be talking about today, how they are stored in a computer. And we did talk about floating points in the lecture, and that we are going to get to that, but that's going to be what we build up to, because it turns out there's a lot of stuff that we have to understand first if we want to understand floating points. So let's begin by first talking about basic binary. First of all, we've talked about this before, but why do we even use binary in a computer? Well, it's fairly simple, because fundamentally a computer is just electricity. It's a circuit with electrons flowing through it, and there's billions of these tiny things called transistors. And if a transistor receives a high voltage, we say it's a 1. If it receives a low voltage, we say it's a 0. So charged or not charged. That's why we have these two states going on in our binary. And actually, scroll back. And that's why we use the binary system anyway. And so far in the lectures, we've been doing some very basic binaries. So, for example, we've seen numbers like 1, 0, 1. And how do we read that? We say there's 2, 0 here, just 2 to the 1. 2 to the 2, and we read it as there's 1 4s, there's 0 2s, and there's 1 1s. So to calculate the value, we just do 4 plus 1, which gives us the value of 5. And that's the sort of binary that we've been messing around with. But as you'll find out throughout this presentation, there isn't actually a lot of information contained within this, and when you store it in a computer, it is actually stored slightly differently. So, firstly, what type of numbers are there even in a computer? So if we split the screen into 4, we can see there are kind of 4 fundamental types of numbers in a computer. The first of which is what we're familiar with. These are unsigned integers. So let's break this down. What are integers? These are real numbers with no fractional part. And what that means is these are whole numbers. They have nothing after the decimal point. So numbers like 5 or 7, 26, a million, these are all integers. And unsigned just means that they have no sign. They're not positive or they're not negative. They just have some sort of value, some sort of magnitude, but we don't know if that's positive 5 or negative 5 or anything like that. And that's why we have another type called signed integers. And these are just literally integers like 5, but with a sign in front of them. So positive 5, negative 27, whatever. But these are also integers. And now in our lecture last week, we did start to talk about numbers such as 0.1. And we said that these are floating point numbers, but we will get to the terminology in a little bit. But of course, we can also represent the same way signed numbers like minus 0.5. And we called them floating point numbers in our lecture last week, but we really don't know what that label even means. But just mathematically speaking for now, we're going to call these fractional numbers. So they have some sort of fractional part. They're not whole numbers, they're not integers, they're like 5.6, 7.2, or for sign, or for, that's wrong, it should be signed fractional there. It should be something like minus 7.5 or whatever, something like that. And we're going to talk more about why they're called floating point numbers later on in this presentation. But for now, let's just begin one by one, going through these slowly, because there is a lot of information that we're going to go through today. So to start simple, unsigned integers, I'm not going to talk about them too much because we already know what they are. This is what we've been doing in our lectures so far, and you can watch week 0, lecture 0, and lecture 1 if you want to find out more about that. Actually, one thing though, if I can go, spoilers, if I can go back to unsigned integers, something that we haven't learned is how to add numbers, how to do arithmetic with binary numbers. And we're going to start off by learning how we can do it with integers. So if I have a number 5, which was 1, 0, 1, and I'm just going to pad these with some zeros to say that we're going to store this in 1 byte, which is 8 bits of memory. 1, 2, 3, 4, 5, 6, 7, 8. And we're going to add this to some number, let's say 9. So that's going to be, if I just write down the place values here to make this easier to read, and so on, I'm going to have 0, 0, 0, 0, 1, 8, 0, 4, 0, 2, and 1, 1 to get 5 plus 9, which add the addition symbol there, and I'll get 1 plus 1 is equal to 2, which is 1, 0 in binary. So what happens is the 1 gets carried over up here, and we add the 0 here. Then the 1 plus 0 becomes 1, we get 1 plus 0 is 1, 0 plus 1 is 1, and the rest are zeros. And our final answer is 8 plus 4 plus 2 plus 0 which is 14, and we know from the decimal system that 5 plus 9 indeed is 14. So that's how addition would work. And another concept that I want to talk about very briefly is the concept of overflow, which we have seen before as well, but we haven't actually seen what it would look like in binary. So let's say we're trying to do the addition, what is this, 13 plus 9, using a 4-bit system. So in this particular computer that we're using, each number or each integer is stored as 4 bits. That's the maximum capacity. So if I get rid of this, let's do the addition. So 1 plus 1 is 2. So I put the 1 over there. 1 plus 0 is 1. 1 plus 0 is 1. And now 1 plus 1 is 2, which is 2 digits. It's 1, 0. But the computer only has 4 bits to store each number. So what ends up happening is this bit is lost. The computer completely ignores it, and it returns to us the result 13 plus 9 equals 6. So the computer thinks 13 plus 9 equals 6, which we know is wrong, and this is an error that we call overflow. And that's what we've seen briefly before, but we haven't actually seen it in work in binary. So that's really all we need to know for unsigned integers for now. So let's move on to the next part, which are signed integers. And as I said, these are the exact same numbers, but just with a sign, a positive or negative sign in front of them. But right now, you may be kind of wondering, how do we actually do this? Because usually when we learn binary, we don't talk about the sign. We never actually talk about how to represent negative numbers or anything like that. And you may be thinking, in the decimal system, we just use numbers like -1. We literally have a sign there, or -7. Why don't we just have, in the exact same way, -1011 to represent -13 or whatever? I think that's 13. So why don't we just do that? Well, the problem with that is the computer, as we said right in the beginning, can only represent zeros and ones, 2 different states. So that's a symbol that we can't represent in the hardware of a computer. But well, you may be thinking, there are 2 signs that we have to work around with. There's a negative sign and there's a positive sign. And we have 2 states that we can mess around with, 0 and 1. So we could say, we can add a 0 right in the beginning. So if we're using, let's say, 8 bits for 1 byte to represent a number, we could just say the first bit is going to be a special bit. Let's call it, let's say, a sign bit. And it's just going to represent the sign of the number. So if it's a 0, it's a positive number. So right now we'd have positive 13. But if I change that to a 1, let's say we're going to call it negative 13, because we have 2 states and 2 characters or 2 signs that we want to represent. And let's actually do that, yeah. So this might actually work, right? And it turns out computer scientists thought the exact same thing initially. So what they developed was a system called sign magnitude, which is where they literally just have the sign or the sign bit, and the rest represents the magnitude of the number. So in this example, if I just write down the base units at the top here to make it simpler, we have 1, 2, 4, 16, and so on. So right now, this first bit is not counted as a number, because usually we'd say this is the 128th value, but we're going to ignore that. So we're actually going to pretend we kind of only have 7 bits to represent the number. So if the sign is 1, so we'll call it negative. The rest is 16 plus 2 plus 1. So the number evaluates to negative 19. Is that correct? That should be an 8. There we go. So the number we will get is negative 11. And that's a system that a lot of computers really early on started to use. But the people who made this hardware started to realize a problem. And the problem is that right now, if you think of any random number, let's say the number 8. And we're using, let's say, an 8-bit system or a 1-byte system. So let's see the positive number 8 is going to be padded with 4 zeros, and then 16, no, 8, 4, 0, 1, 8, 4, 2, 1. So we'll have 1, 0, 0, 0. And then the number negative 8 will be 1, followed by all these numbers, 1, 0, 0, 0. So once again, the only difference here is the sign. So we have positive 8 and negative 8. Everything else stays the same. So we know that when we add the numbers of 8 plus negative 8, we should get the result 0. So computer scientists put this to the test. So let's add these numbers, 0, 0, 0. The 1 gets carried over, 1, 0, 0, 1. And we end up getting the number, if I fill in the remaining units here, we end up getting the result 8 plus negative 8 equals negative 16, which we know for a fact is incorrect. So in the hardware of a computer, if you try to do calculations using the sign magnitude system for integers, it doesn't work. We get incorrect answers such as minus 16. So computer scientists said, hey, we're going to scrap the system altogether and start once again. So they thought, how about we just flip all the digits, so all the bits. So if we had a number, let's say 0, 0, 0, 0, 1, 0, 1, 0, which is the number, if I write these down, which is the number 10. To represent negative 10, actually that's confusing because there's ones and zeros. I'm going to change that to 1, 1, 0, 0, which is equal to 12. So if you wanted to represent the number minus 12, computer scientists said we're just going to flip all the bits. So if it's a 0, it becomes a 1. If it's a 1, it becomes a 0, and so on and so forth. And this is a system known as 1's complement. And the reason that it's called 1's complement is, well, to understand it better, we need to think about what a complement actually means. So using the decimal system, which we're all familiar with, if we say we want the 9th complement of 6, we just literally do 9 minus 6, which gives us the answer 3. If we did the 9th complement of 5, we get the answer 9 minus 5, which equals 4. So the reason it's called 1's complement is if we just had this number here, 0, 0, 0, 0, 1, 1, 0, 0, to each individual bit, we just do 1 minus that digit. So we do 1 minus 0 to get 1, 1 minus 0 to get 1, 1 minus 1 to get 0, and so on and so on. And that's why it's called 1's complement. We're literally just getting the complement of 1 for every individual bit. But the thing is, you might have spotted this already, there is actually a problem with this system as well. In the exact same way as the sign magnitude, if you try to add these two numbers, we end up getting a weird answer. So 0 plus 1 is 1, 1, and we keep going, and we end up with all 1s. And if you think deeper about this, if we put any number, so I'm not even gonna think about the value of this. How do I go back? I'm just gonna write down 1, 0, 1, 1, 0, 0, 1, 0. If we flip all the bits and try to add these two numbers together, we're always gonna get the same 1, 1, 1, 1, 1, 1, 1, 1, 1. And the reason for that is because the way we actually derive this is by getting the 1's complement, and that's why this works. And the problem with that is, at this point, we have two ways of representing 0 in the 1's complement system. So having all zeros would represent the number 0, but having all 1s would also represent all zeros. And computer scientists said, you know what, the system has faults, but it kind of works, so we're going to start using this. So old computers, once again, there are computers that used 1's complement before as well. But there's a lot of issues if you have two repeated numbers that represent the same value. So they both represent the value 0. So when the computer tries to perform other kind of arithmetic, it can run into a lot of errors. And computer scientists thought, you know what, there must be a better way we can do this. And another thing to note is that having two different ways of representing the same number is quite wasteful in the computer's memory because it has a finite amount of space. You want to maximize it for higher efficiency. And if we go back to this number chart, which was seen before, we can see this is how the numbers are represented. To represent 0, we do all zeros or all 1s. There's two ways of representing it. To represent 1, you just do 1, and all the positive numbers are the same as we're familiar. But all the other numbers, all the negative numbers, we literally just flip the bits to get the 1's complement. And as you can see, we have the repeated 0 here, but everything else seems to be fine. So what if we could somehow shift all these numbers to the left by 1 so that all the numbers can only be represented by one specific pattern of bits? And that's exactly what computer scientists did by developing what's called the 2's complement method. And the way we work out the 2's complement of a number is actually very, very simple if you know how to get the 1's complement. So if you have the number 7, let's say, we're using, let's say, an 8-bit system. Once again, it'll be 1, 1, 1, because 1 plus 2 plus 4 is equal to 7. To get the 2's complement of this, you'd have to firstly flip all the bits to get 1, 1, 1, 1, 1, 0, 0, 0. And because we want to shift all these numbers over to the left by 1, we simply just have to add 1 onto this number. And we get 1, 1, 1, 1, 1, 0, 0, 1. And in the 2's complement system, this number would equal minus 7. So if we're given the positive number of 7, we know how to work out the number minus 7. But what if we want to go the other way around? Well, the process is actually very, very similar. So let's say we're only given 1, 1, 1, 1, 1, 0, 0, 1, which is minus because the way we derive this is we flipped all the bits, then added 1. So if you want to get back to the positive number, you simply just have to take away 1 rather than add 1. So we know 1 minus 1 is 0, and the rest is just the same. And then we just flip all the bits, like we did over here. So we get 0, 0, 0, 0, 0, 1, 1, 1, which we can read as the number 7. But the reason that we know this is a minus 7 and this is a positive 7 is by looking at the first bit. So for this number, it's 1, 1, 1, 1, 1, 7. So the computer just sees the first bit, it's a 1, it knows it's a negative number, so it knows it has to go through this process to work out its magnitude, and because it's a 1, it's just that it's negative 7. But if it's presented with just this value, 0, 0, 0, 0, 0, 1, 1, 1, it sees the 0, it knows it's a positive number, and just uses the normal way we work out binary. We do 2 to the 0, 2 to the 1, 2 to the 2, and so on, to work out its magnitude. You look like you have some questions.
So obviously the majority of computers don't store numbers, integers as it were, in 8 bits.
And of course.
They store them in, say, 4 bits.
Yeah.
Sorry, they store them
Like
in 4 bytes.
Yeah.
So in that sense, where's the 1 at the end?
The 1, it's always, so if we're using 4 bytes,
Yeah.
so let's just say this is the first byte, and then we have the rest of the bytes over here. It would just always be the one at the very left would be the signed bit. So if it's 0, we say it's a positive number. If it's a 1,
But what I don't understand is how it gets to that. So if you represent, if I drew the number 7, which is the top one there, 1, 1, 0, 0, 0, 0, 0.
Yeah.
Right, okay. So if I now want to represent that as a negative number,
Okay.
but I am using a 4-byte system,
Okay.
then how does that 1 end up all the way over there?
So if it is a 4-byte system, this number itself would also be stored in 4 bytes with a bunch of trailing zeros until it reaches 32 digits.
Yes.
And then because this is all zeros, we know the very left is 0.
Yes.
So when it flips, it'll become a 1. And that's why, and when we have a bunch of 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 0, 0, 0, right?
Now that's taken it to 1's complement.
Yeah, this is 1's complement.
Yep.
Then we got to add 1 onto it.
Yep.
And this is just only going to change the first. 0 plus 1 is 1. The rest stays the same. And it's all 1s with a 1 at the very end. So the computer only has to look at the very last one. But of course, this is kind of a waste of space at this moment because we only really need up to this many digits to know that that's positive and that's negative. But if a computer system uses 4 bytes, it would store it at padded with all zeros or all 1s. So cool. So that, what was I talking about? 2's complement. So if I can just get rid of this.
So the biggest number that you could store with a
So if we use a 2's complement, let's say with 8 bits, if I can just draw this out.
well, the biggest number that you can store with 8 bits is 255.
255.
But if let's say that you were using signed integers,
Using the 2's complement.
then it would simply be 127. You'd be able to store a range of 127 positive to 127 negative.
Oh, wait, if we're using 2's complement,
Yeah.
it's implied that we're using signed integers,
Yeah.
right? So if we have 8 bits, and the first is a signed bit, the maximum number we'll be able to get is this being a 0 because it's positive, and the rest being 1s, right? So as you said, that's 200, is that 100?
127 there, isn't there? So if you use the one on the far left, that's
Yeah.
120. Sorry, 200.
I just didn't write this out just for my sanity.
128.
Yeah, so we get 128, sorry, as the largest number we can get.
Yeah.
And let's just say this is some number that we're getting, or x, or n, or actually let's call it x. And the smallest number we could get is if this was a 1, and we have to change all of these. Actually doing this on the fly. We have to flip everything, so you get, and then we gotta take away 1 from it, and then flip everything. Gotta take away 1 from it.
Let's stay exactly what I want to see. This is.
But it's something like 2n minus 1 minus 1 or something like that. Like something like that. I can't remember the actual bit
But
sequence.
wouldn't it be minus 128?
Minus, it would,
Is that
actually, this is wrong. This is 127, and this would be minus 128. Because 0 is counted as this 128, and this is counted. Because basically, if you have 8 bits, you can store two of the 8 different combinations, which is 256, right?
Yes.
So if we think from 0 to 127 is 128 numbers, and then from minus 1 till minus 128 numbers there. So yeah, something like that. I can't remember the actual sequence.
No, that's brilliant. That's what I want to know.
So that is 2's complement, and something that's really good about 2's complement is actually a lot of good things. So first of all, if I just put down a random number again, let's say we start off with the number 5. Whoa, the number 5, which equals, let's say 0, 0, 0, 0, 0, 1, 0, 1. And then to get the actual 2's complement value, we flip all the digits, and then we add 1 onto it, so negative 5 will be this. If we only had this, we could take away 1, then flip all the digits. But something else we could do, another neat trick, is we could actually just put all the base values. I'm just going to put this down here now. We could put in 1, 2, 4, 8, 16, 32, 64. But for the last one, we simply just have to put in the value minus 128. So we can get, to work out this value, we do 100 minus 128 plus 64 plus 32 plus 16 plus 8 plus 2 plus 1. So I'm going to just do this. That becomes minus 64. That becomes minus 32.
We start with 4.
Minus 16. Yes. No, because it's a 0. Just to, yeah. So if I add that, there's minus 8. If I add 2, minus 6. If I add 1, we get minus 5. So that's another way of reading 2's complement numbers. And there is a reason why this works, which you may be wondering right now. And the reason this works, the short answer, is because of overflow. The computer programmers who thought of this said, overflow is kind of an annoyance to us, but we could turn it into a feature. And the way that works is, let's say we're using 3 bits to represent a number. Just 3. 1, 2, 3. And that would have 2 to the 8 different combinations, right? So we could write down all the possible values. So 1, 2, 3, 0, 1, 2, 3, 4, 5, 6, and 7. And that's 1, 2, 3, 4, 5, 6, 7, 8 different combinations that you can represent with 3 bits. And if we picked a random number here, like 2, and we want to add 1 onto it, we just have to move over in the clockwise direction by 1. So 2 plus 1 becomes 3. 2 plus 3 becomes 1, 2, 3, gives us 5. So the reason that I put it in a circle like this is because in the computer, due to overflow, if we have, let's say, the number 7, and we try to add 1 to it using a 3-bit system, the computer won't be able to give us the answer 8. Instead, it'll give us the answer 0. So because it kind of has this effect of wrapping around, 2's complement works. And we're going to actually see that with an example. So if we have the number 7, let's say, and we want to do 7 minus 7, which we know should give us the answer 0. But we can also do 1, 2, 3, 4, 5, 6, 7. We can also get that same answer by doing 7 plus 1. And we can do these for other numbers. 1 equals 7 minus 6, which equals 7 plus 1, 2. And we can keep going. 2 is 7 minus 5, which is 7 plus 3. And we can keep going on and on. What you will notice here with these numbers is a cool pattern. Because we're using 3 bits with the maximum number, that should be a 3, or the maximum number of 8 different combinations, we can see that these numbers over here are quite cool. So if you wanted to perform the calculation 7 minus 5, let's say, computers don't actually inherently know how to minus things. They only know how to add things. So what we can actually do is 7 plus the 8th complement, because there's only 8 possible combinations I'll just write this out. The 8th complement of, 5, which equals 7 plus 8 minus 5, which is 3. And as we know, we go from 7 to 1 to 3. Because it has this wraparound effect, instead instead of going on to 8, 9, and 10, it goes back to 0, 1, 2, which gives us the correct answer. And that's how it turns out computers, when they use a 2's complement system, they actually minus numbers by adding numbers. They work out the complement of that number. So if we're using 4 bits, that would become the 16th complement of whatever number you're trying to minus. And actually, going back to the name 2's complement, it's kind of a strange name because the 1's complement is pretty straightforward. We just, to each individual bit, we perform a 1's complement. We do 1 minus that bit. But if we have some sort of number like 1, 1, 0, 1, 0, let's say, which is the number 5, and we perform 2's complement on it, 2's complement on it, and we try to do the same thing as we did with the 1's complement. So 2 minus 1 would give us 1. 2 minus 0 would give us 2, which is, we really don't know how to represent that. Let's just carry it on for now. 2 minus 1 is 1, so we kind of add the 1, and it becomes really weird. We don't end up getting the actual number that we get. So name 2's complement is quite mysterious, and to be honest, I don't know exactly why, because the internet provided some very unsatisfactory answers, but after thinking about it, if we go back to that 3-bit analogy, and we know that 7 minus n, some random number, is just equal to 7 plus the 8th complement of n, right? So the 8th is actually, if we put the place values on, is the next highest kind of place value, if you will. And we're kind of just getting the complement of that number, but that number can change depending on how big your system is. If we're using 8 bits, you're going to get the 256th complement. And because that number can always change, we can't keep calling it the 8th complement or the 256th complement depending on the digits. So I think programmers just decided to call it 2's complement. But that's just a theory for me. I'm not sure if that's actually true. But now we should have an understanding of what 2's complement is. So now we know how to represent signed integers using how they're represented in a computer. So let's start talking about fractional numbers. And this is where things get a little bit more interesting. And we actually started talking about this in the last lecture, where we kind of just gave some random examples. Like let's say we had the number 101 or 101.11. The way that we would find out the value of this number is just by putting the place values. So after the decimal point, we put in 1, then 2, then 4, and so on. But to the right of it, we just put in a half or a quarter. And the way we derive that is because the base is 2 to the 0, 2 to the 1, 2 to the 2 going to the left, and to the right, let's go 2 to the minus 1, 2 to the minus 2, and so on. So if we actually wanted to work out this value, we do 4 plus 1 plus 0.5 plus 0.25, which gives us the answer 5.75. And we kind of saw this in the lecture, and it's very, very similar to how we work out normal integers as well. So this should be quite intuitive. So if I can just give another example, which I wrote down somewhere in here, fractional number. Yeah, let's just give another example, just to practice our skills. So 10.01 would give us the answer of, I write down the values once again, 2 plus 0.25, which equals 2.25. So great, now we know how the number system actually works. So how is it stored in binary? Well, the problem with, the kind of immediate problem that we can see is that there's no way to represent this decimal point. So if we have, let's say, an 8-bit number, like this, we can't reserve a bit for that point because we can only have a 0 or a 1, right? And because there's a sequence of 0s and 1s already, which already have some sort of meaning, we can't just say this specific 0 is going to equal a point. Because a computer can differentiate from that 0 to this 0, or this 0 to that 0. So what computer programmers first did was, let's say, when they actually built the computer themselves, or when they actually built the hardware, they said, you know what, whenever we're dealing with fractional numbers, we're just going to say the point, there's going to be an implicit point at, let's say, this random point over here, after the 5th bit from the left. There's always just going to be a point there. And the way they did this was just when they actually made the computer, when they designed the system's architecture, that's how they built the actual transistors themselves. They just said there's an implicit decimal point at this point. And this is fixed for any decimal point that we're going to see. So if you want to represent the number 5.5, which we know, 5.5 is going to be equal to 101.1. So we just pad the rest of the zeros and say 101.1 and pad the rest of the zeros once again. If you want to represent another number using this specific system, which has the point after, is that 8, 1, 2, 3, 4, 5? Actually, I was going to use a different color for this. Say, this is the point, let's say, is going to be fixed after the after the 5th bit from the left. So if you want to store the number, let's say 7.05, the 7.125, let's say, we just get the number 7, which is 111. I think 1 plus 2 plus 4, yes. 0.001, because 1/8 is equal to 0.125. So we just put in the numbers 111. There's an implicit decimal point there, hard-coded into the actual hardware, and then put 0, 0, 1, and pad the rest with zeros just as so. But there's a problem here, because let's say we want to represent the number, oh, I actually don't know what a 16th is. I'm going to quickly search that on my phone if I can. But while I do this, just imagine we wanted to represent the number 1/6, which I will get the value of right now. The number 0.0625. We know that in binary it is a 16th, so we're going to have to do 0.0001. So using this specific architecture, which has 8 bits assigned to each fractional number, and the point is always going to be after the 5th bit from the left, and we try to represent this number. We put in the 0 here. Cool, there's a point 0, 0, 0, and we need to put in the 1 there. But we can't. But the thing is, we have these 4 bits that are completely unused. They're just going to be padded with zeros. So we do have space that we could use, but because the point is fixed there, we can't actually be dynamic with our numbers. We can't go past 3 decimal places, even though we're not using any of these bits. And that's the big problem with these type of numbers. And by the way, if you haven't guessed, because the point is fixed in these numbers, this system is called the fixed point system. And the numbers work well, the math, the arithmetic works perfectly fine. There's nothing wrong with it. Just the big problem with this system is that there is no dynamism. You can't move this, and a lot of bits end up getting wasted. So what if we could have some sort of system which kind of cares about the context that we're using in it? So if you want to get a really small number, the point will kind of move over to the left, so we can utilize more bits. If you want to make a really big number, the point kind of moves over to the right, so we can represent more numbers there. So like for example, if we're trying to measure the distance between the Earth and the Sun, it's a really big number. We don't really need all the bits after the point. We only need kind of the most significant figures. So the point will kind of float over to the right. Or if you want to measure it to the size of an atom, the point floats over to the left to give us more precision. And because in this system, the point is kind of floating about, we use a system called unsigned fixed point. Oh, before we get onto that, this is getting exciting, but unsigned fixed point is if we just have fixed point, which is unsigned, it's just like normal binary. So if we saw the number just 101 point, like if you look at this byte and say that it can count up to whatever the highest number is, and there is no such thing as a signed bit when we're using an unsigned system. So the highest number that we'd be able to represent would be a 1, 1, 1, 1, 1, with an implicit point, then 1, 0, a 1, 1, 1, which would give us the value of something really, not that big actually, but some value. But if we're using signed fixed point, there's actually a few different ways that we can go about it. We can use the exact same way as we did for integers. We can use the sign magnitude method, where the first digit represents the sign and the rest represents the magnitude. So if we're using, let's say, a computer which uses 8 bits per number, That's nice. So 1, 2, 3, 4, 5, 6, 7, 8. And we say the point is always going to be at the 5th from the left over here. And we reserve this specific bit as the sign bit. So we just literally do it. If we want to represent the number -5, we just put in the 1 for minus, and then we fill in 1, 0, 1, minus 5.5, let's say, then the rest as so, because that's a 4, 2, 1, and that's a half. We get 4 plus 1 plus 0.5, which equals 5.5. And we just pad this remaining bit with a 0 as so. If we wanted to represent the +5, we just have to put in a 0 over there. That's quite simple, but we can also actually use 2's complement for fixed point as well, and it works exactly the same way. We just have to consider the fact that there is a decimal point there, but we're not actually going to go into that because of kind, but it's exactly the same thing. It's literally the same, and we are gonna kind of revisit it very soon as well. So let's finally move on to floating point, which is what we really want to know about. This is the kind of interesting one. How do we get this float or this point to kind of float around and kind of move? Well,